So I got this nice open-ended problem from a viewer today that I thought I'd like to show you guys because it's pretty nice. But maybe before we look at this, I'd like to reiterate the fact that we have a goal of reaching pi 100,000 subscribers by the end of the year. So the channel assistant really thinks that this is possible, but I'm a little worried that it's not given our analytics. But let's see who wins. Let's try to actually make him win, because if he wins, then we all win, right? Okay, so anyway, let's look at what we've got. So we have the square root of 2 minus 1 to the 0th power is the square root of 1 minus the square root of 0. Well, that's clearly equal to 1. The square root of 2 minus 1 to the first power is the square root of 2 minus the square root of 1. The square root of 2 minus 1 squared ends up being 3 minus 2 times the square root of 2. You could get that just from foiling that out. But interestingly, we can write that as the square root of 9 minus the square root of 8. You can cube the square root of 2 minus 1, and you end up with, let's see, 5 times the square root of 2 minus 7, but then you can rewrite that as the square root of 50 minus the square root of 49. So I think you see where we're going here. You can write, or it seems like you can write all of these powers of root 2 minus 1 as the square root of a number minus the square root of 1 less than that number. So I've written that down here. So it seems like the square root of 2 minus 1 to the n is square root of orange box minus square root of red box, where orange box minus red box equals 1. And that's in fact what we're going to show in this video, that this is actually true. But we need to write this question down a little bit more carefully first. So I'm going to do that by defining the following two sequences of numbers. So I'll call them an and bn, where, let's see, a1 is equal to b1, which is equal to 1. And then the square root of 2 minus 1 to the nth power is equal to minus 1 to the n times a sub n times the square root of 2 minus b sub n. So in other words, this sequence of integers is defined by this expansion of root 2 minus 1. I have this alternating bit in here because, as you see here, the perfect square moves from being on the right to the left. So right, left, so on and so forth. So that just puts it forward or backwards of the other kind of integral term. Okay, so let's maybe see if we can get a nice recursion for these two sequences. Well, notice that we'll have minus 1 to the n plus 1 times an plus 1 times the square root of 2 minus bn plus 1 is exactly equal to root 2 minus 1 times root 2 minus 1 to the n, but we can express root 2 minus 1 to the n like this. So we've got minus 1 to the n, and then an root 2 minus bn. So something like that. And now we can simplify this a little bit. So notice that we could take this minus 1 to the n and cancel it with this just to get a minus sign. So that means our left-hand side is bn plus 1 minus an plus 1 times the square root of 2. Then what does the right-hand side look like? Well, let's multiply it out. So we've got root 2 times an root 2. So that's going to be 2 times an. Then we have negative 1 times negative bn. So that's going to be plus bn. And then we'll have stuff that has a coefficient of the square root of 2. So we'll get that from multiplying the square root of 2 with this minus bn, and then this minus 1 with this an times the square root of 2. So in fact, that'll be equal to minus an plus bn times the square root of 2. Just like I said, by multiplying that out. But now we'll use the fact that the set containing 1 and the square root of 2 form a basis for a vector space of Q adjoin root 2 just to set these coefficients equal to each other. So that's just a fancy way of saying that because The only thing with the coefficient of root 2 over here on this left-hand side is bn plus 1. And the only thing on this right-hand side tells us that we have bn plus 1 equals 2an plus bn. And likewise, the thing with the coefficient of the square root of 2 over here on the left-hand side is an plus 1. Well, really minus an plus 1. And then over here on the right-hand side is an plus bn, tells us that an plus 1 is equal to an plus bn. Great. So now we have this kind of system of one-step recursions for our defined sequence. Okay, great. So now let's see if we can take this sequence of defined recursions and rewrite this like little it seems like in terms of our sequence and then prove it. So in the last board, we defined this pair of sequences, an and bn, by the expansion of the square root of 2 minus 1 to the nth power. And we got that that same sequence can be defined by the following linear recursion. We have a1 is b1 is 1, and then we have an plus 1 equals an plus bn, and then we have bn plus 1 equals 2an plus bn. And then in fact, from here, we can use a couple of different methods, including a matrix method, to get a closed form for an and bn, which will actually solve this problem. But that's not what we're going to do. We're going to solve this problem a little bit differently, maybe without finding a closed form for an and bn, just because I think it's nicer. But before we do that, let's take this version of an and bn and write it so that we can like rephrase this question. But in order to rephrase this question, we need stuff under the square root for both of these terms. So let's see. That means we're still going to have this minus 1 to the n out front. And then here we'll have the square root of 2an squared, if we want to bring this an inside, minus the square root of bn squared. Great. And so that puts it so that we have the square root of something minus the square root of something else. And now we can rephrase this seems like question pretty nicely in terms of our sequence. And I'll write that as a claim. So for all natural numbers n, we have, well, we want orange box minus red box to be equal to 1, but notice that that built into the whole situation, everything switching from where the perfect square is, which we've built in with this minus 1. So we'll actually need to include an absolute value here. So the absolute value of 2an squared minus bn squared is equal to 1. So just to reiterate, this is like our orange box minus our red box equals 1, just with the kind of alternatingness pulled out. Okay, so how can we prove this? Well, I think maybe our best bet is a proof by induction. So for a proof by induction, we need to first do our base case. But notice the base case will be the n equals 1 case, and the n equals 1 case follows immediately. Notice 2a sub 1 squared minus b sub 1 squared is 2 minus 1, which is equal to 1. That's good to go based off of our seeds here, or really just this line right here. Okay, so from here we can make an induction hypothesis. So let's suppose for some k bigger than or equal to 1, we have the absolute value of 2ak squared minus bk squared equals 1. So we suppose the kth case is true, and now we'll work on the k plus first case. So let's consider the absolute value of 2ak plus 1 squared minus bk plus 1 squared. Great. Now we'll use our recursion to write ak plus 1 and bk plus 1 in terms of ak and bk. So that gives us the absolute value of 2 times the quantity ak plus bk squared minus 2ak squared plus bk squared. So 2ak plus bk quantity squared. So that's looking pretty good. So now let's multiply that out. So multiplying this term out will give us 2ak squared plus 4ak bk plus 2bk squared. So I distributed that 2 through while I was at it. Then multiplying this thing out will give us minus 4ak squared, and then minus 4ak bk, and then plus bk squared. And I should say that's minus bk squared because I distributed my minus sign through. And all of this is inside of absolute values. Now let's notice that this term cancels with this term, which is good news. And then from there, I can cancel some things out. So let's notice that I've got 2ak squared minus 4ak squared. So that gives me negative 2ak squared. And then I've got 2bk squared minus bk squared. So that gives me plus bk squared. But notice that this expression right here is exactly negative 1 times this expression, which is inside of these absolute values. The absolute value of this is 1, which means the absolute value of what we have left over here is also 1. But that's exactly what we needed to do to finish off this induction proof. And that's a good place to stop.